Welcome everybody to this special Thursday edition of Compass seminars. Today we have Kurt Hansen presenting his 1-hour seminar, so this is pre-defense. Kurt is a 5th-year PhD student with Sharon Majumdar, and Ben Kurtman, Dave Nolan, and Patty Pigeon make up his committee. He graduated from University of Albany with a Bachelor of Science in Atmospheric Science and minors in Mathematics and Computer Science. He's won numerous awards while here at RSMAS, including the TA Excellence Award and the Miami Graduate Fellowship. He was also a 2015 AMS named scholar and a NOAA Halling Scholar in 2014. He's been involved with a lot of service here, including being chair of Grad Out, MSGSO, Canes on Canes, and the Hurricane Research Division map discussions, and he's also presented at numerous AMF's conferences over the past years. Today, he'll be talking about use of vertical wind shear in subseasonal prediction of Atlantic tropical cyclone activity. All right, Kurt, so off you go.
All right, thanks, Anne. Let me just get my screen shared and my PowerPoint going. All right, so as Anne said, I'm going to be talking to you about the use of vertical wind shear in subseasonal prediction of Atlantic tropical cyclone activity. So perhaps the most important word, and perhaps the word you're least familiar with in that entire title, is subseasonal. So subseasonal is sort of an awkward timescale in between weather scales and seasonal and climate scales. And so the time frame of subseasonal forecasts is usually 2 to 6 weeks. So beyond weather, before seasonal, so subseasonal. So subseasonal predictions right now aren't very good, but they are really important. They're important for things like emergency preparedness, transportation, shipping, energy, and many other sectors of the economy. Hurricane activity is of particular interest for subseasonal activity. One, because hurricanes are highly impactful events, as we've seen, unfortunately, quite a bit of this year, but also because hurricane activity has a large amount of subseasonal variability. So the main goal of my work is to see if we can improve upon subseasonal predictions of Atlantic tropical cyclones, or TCs. And so I'll be saying TCs a lot. That's just the generic term for a hurricane. So to kind of give you an example of the kind of variability that I want to predict, here's sort of a case-by-case from this year. So from July 21st to August 5th this year, so this time frame is typically before peak hurricane season in the Atlantic. So there's normally not much going on. But this year, we had 4 tropical cyclones form in the tropics, 2 of which became hurricanes that impacted the US, causing billions of dollars in damage. However, the following 2 weeks after this period, so August 6th to 19th, this is where climatologically, normally we see a ramping up of activity in the Atlantic. However, this year we saw fewer tropical cyclones and weaker tropical cyclones, less impactful tropical cyclones. And so this was maybe a bit counter to what we would have expected climatologically. And so this is the kind of variability that I want to predict. I want to be able to say, is this upcoming 2-week period going to be one where there's multiple hurricanes in the Atlantic, or is it one where we're only going to see a measly tropical storm? So the gap. To approach subseasonal predictions, usually forecasters or researchers come from one of 2 directions. They either approach from the weather side of things or the climate side of things. And there's problems with both of these approaches. So if you're coming at a subseasonal prediction from a weather perspective, you have to deal with the fact that weather models lose skill very quickly. So Komarami 2014 showed that prediction of most environmental variables lose skill within 10 days, if not sooner. And tropical cyclones certainly fit into this. Tropical cyclones are small and they're complex. They extend throughout all layers of the atmosphere. And therefore, they're prone to large errors and biases on subseasonal timeframes and even on weather timeframes. So TC subseasonal prediction from weather models is going to be complicated. the other way we can approach this is from more of a climate perspective. And so this includes looking at long-term oscillations and seeing how those impact hurricane activity. So for instance, hopefully you've heard of the El Niño Southern Oscillation, or maybe you've just heard of El Niño. This can impact hurricane activity in the Atlantic. However, the problem with using climate factors is that most of them vary over really long periods of time. So for instance, El Niño changes really slowly, and it doesn't give us any information on week-to-week variability. So like nothing's changed with El Niño in the past week or month that we already didn't know. So we can't actually use that to say what's going to happen next week that's different than the previous week. So I'm going to go over a few important factors that impact tropical cyclones on all sorts of scales. So I'm going to start with the smallest weather scales. And the most important factor, and of course the topic of this talk, is vertical wind shear, or just shear. And shear is the difference in wind speeds at different levels of the atmosphere. For hurricanes, the level of shear that we use is 200 millibar minus 850 millibar shear. So that's like the winds at the very top of the atmosphere minus winds that are closer to the surface but not actually impacted by the surface. And so the higher the shear, the less tropical cyclones tend to develop. And this is because if you have winds blowing in different directions, it tends to rip storms apart. So shear is bad for tropical cyclones. Some other factors that I've looked at are sea surface temperatures, or SSTs. And these are important because warm ocean temperatures are the fuel that are needed for hurricanes. So this is actually perhaps the most important factor for tropical cyclone activity, at least on weather scales. Some other factors that I looked at are vorticity, which is a fancy term for the spinning of the atmosphere, and that kind of intuitively connects to the development of hurricanes. And another factor is relative humidity, or RH, and that is a measure of the amount of moisture in the air. Of course, if the environment is too dry, then thunderstorms can't develop, and hurricanes will either lose organization, or if it's really dry, hurricanes can be prevented entirely. So next, we're looking at factors on subseasonal scales. And for the interest of hurricanes, there really is only one, and that is the Madden Julian Oscillation, or the MJO. And because this oscillation is really the only thing in subseasonal town, it is incredibly important for any subseasonal prediction. So what is the MJO? The MJO is a 20 to 60 day oscillation in convection over the Indian Ocean and Pacific. And when I say convection, I mean thunderstorm activity generally. And so we can see this sort of oscillation of thunderstorm activity in this animation on the right, where we see these blues indicate a large amount of thunderstorms moving from the Indian Ocean and then over into the Pacific. So this kind of gives you a sense of the scale. This MJO is like a continent size worth of thunderstorm activity that's moving very slowly over the ocean. So to measure the MJO, we separate it into phases 1 through 8, although the MJO can also be inactive or neutral if thunderstorm activity isn't clustered into these these continent-sized blobs. So MJO phases 1 and 2 see the most TC activity in the Atlantic, and MJO phases 1 and 2 are associated with thunderstorm activity over the Indian Ocean. So you might be wondering how come thunderstorms in the Indian Ocean impact tropical cyclones in the Atlantic? Well, one thing to remember is these are really large area of thunderstorms, and so these create circulations that impact weather all over the globe. And in particular, the MJO influences Atlantic TC activity through a variety of debated means. So some studies have shown that when the MJO is in phases 1 and 2, it enhances vorticity over the Caribbean. It can also increase relative humidity over the Atlantic, and it can also decrease shear. Another way that the MJO might influence tropical cyclone activity in the Atlantic is by enhancing African easterly waves. And these are very intense but relatively small clusters of thunderstorms that move over Africa and into the Atlantic, and then can develop into hurricanes. So if the MJO amplifies these waves, that means that there's a stronger seed for hurricanes to develop. And finally, some seasonal factors. So these are the factors that change really slowly. So even though these don't actually vary on subseasonal timeframes, they're still important because they can impact subseasonal scale. So the one that you've heard of and the one that I brought up earlier is the El Niño Southern Oscillation, or ENSO. And it is a 2 to 7 year oscillation in East Pacific SSTs. So in the warm phase of ENSO, or El Niño, the water temperatures here off the coast of South America are very warm, and this creates a circulation that increases shear over the Atlantic and causes fewer hurricanes to form. And conversely, during a La Nina, or the cool phase of ENSO, there's less shear and more hurricanes tend to form. Another variable that varies on seasonal time scales are SSTs in the main development region, or MDR. And so the MDR is a region of the Atlantic in between Africa and the Caribbean. And sea surface temperatures are particularly important here because this is where a lot of hurricanes get their start. And in fact, most hurricanes and most major hurricanes develop over this region. And so if the sea surface temperatures in this area are much warmer, that helps with development and can help with storms later on. So warmer MDR SSTs leads to more tropical cyclone activity in the Atlantic. So now that we know the factors, let's look at the current state of subseasonal prediction in the Atlantic and where these subseasonal predictions are drawing their skill from. And so what I have here, this is a plot from Levi-Cowan's Tropical Tidbits showing vorticity. So this forecast was made about 10 days ago, and it's valid today. And so this GFS forecast shows a bunch of vorticity in the Caribbean, indicating tropical cyclones near Mexico and near the Lesser Antilles. Now, this forecast didn't pan out because it was a really long-range forecast. But even though these two tropical cyclones don't actually exist, this could potentially be considered an accurate forecast because there is a tropical cyclone over Florida right now, and there is a tropical storm out in the middle of the Atlantic, and there is a storm that's likely to develop in the Caribbean very shortly. And so this long-term prediction could be considered accurate in the sense that the model captured that there would be tropical cyclone activity in the subseasonal range. And so one of the themes of this talk is for subseasonal forecasts, you need to really lower the bar. Another subseasonal forecast, this one is produced by the Climate Prediction Center, and they forecast a bunch of things on weekly scales, including temperature and rainfall. And they draw their predictability from a lot of different sources. So they look at ENSO state and MJO, and they also look at what the models say is going to develop. So we can see this forecast is months ago, that the CPC was indicating that tropical cyclones were likely to develop over the Atlantic during this late August, early September period. And finally, Phil Klotzbach in Colorado State releases a subseasonal forecast every 2 weeks during the peak hurricane season. That's a lot of text, so there's not like a fun graphic I get to show you, but they draw from a whole bunch of different sources of information. They look at the National Hurricane Center prediction, the models, as well as the MJO, ENSO state, and sea surface temperatures. And so one of the things they look at is the MJO, and this is a Wheeler-Hendon diagram. And so this tells us where the MJO is and roughly where it's forecasted to be. And so this red line shows the previous history, and so this red line, when it's in phases 2 and 3 or the Indian Ocean, indicates that there's convection or thunderstorm activity in this region. And we can see that the MJO for this forecast period moved into phases 4 and 5, which means that there's thunderstorm activity over Indonesia. And this green line indicates the forecast. And this ECMWF forecast shows that the MJO is going to be neutral and then eventually reappear in phases 8 and 1. And so based on this forecast, we might be able to say that 2 weeks from now, the MJO is in a favorable phase for Atlantic tropical cyclone activity. And so this is the kind of thing that Phil Klotzbach looks at. So the goals. So we saw these forecasts. What was maybe something that they were missing? And so my goal is to find out what sources of predictability maybe we haven't drawn from yet, and maybe if we can use those for forecasts. And so there are, the first thing that I want to test is, are there signals for Atlantic TC activity based on broad and hopefully more predictable environmental conditions? And so I said before that Komarumi showed that environmental conditions aren't predictable beyond 10 days, but a caveat for that is that if you take an area average, so say if you take shear over the entire Atlantic basin, that will hopefully be a more predictable variable than just instantaneous shear. So by taking an area average, you can get predictable environmental conditions. And so my hope is to find some environmental conditions that are associated with TC activity on subseasonal scales so that we can maybe use them for prediction. Another thing I'm going to look at are the nonlinear impacts of climate oscillations. So in particular, I'm going to see how does the MJO and ENSO interact with each other, and how might those interactions influence tropical cyclone activity in the Atlantic. And then I'll try to see if we can use those to predict some tropical cyclone activity. So methods. So the data I'm using a lot of different data. So for reanalysis, reanalysis is our best guess for what the atmosphere used to look like. So we don't have observations everywhere all the time, so we have to make a reanalysis data set. And I am using the ECMWF reanalysis data set 5 or ERA 5. And I use this to get wind data, MJO data, which I'll go over in a bit, SST data, as well as relative humidity and vorticity, and whatever other environmental parameters I'm looking at. It has 3/4 of a degree resolution, and it has daily data, or I'm using daily data from August through October from 1979 to 2019. For my forecast, I'm using hindcasts from the Navy-ESPC, which is part of the SubX project. It has a 1 degree resolution, and I'm using over 300 45-day predictions from 1999 to 2016. And so I'm going to go over that in more detail when I get to my prediction section. And finally, for my tropical cyclone data, I'm using the International Best Track Archive for Climate Stewardship, or IBTRACS. And this gives us the wind speed, the maximum sustained wind speed, and the position data for all Atlantic tropical cyclones at 6-hour intervals. And I'm using this over the 1979 to 2019 period. And I use this data to calculate accumulated cyclone energy. So accumulated cyclone energy, or ACE, is my measure of tropical cyclone activity. So if you get nothing else from this slide, just remember when you see ACE or when you hear ACE in the rest of this talk, think tropical cyclones. Or if you don't remember tropical cyclones, just think amount of hurricanes. And so ACE is defined by this equation here, which is actually pretty simple as far as meteorology goes. But what this means is that to calculate ACE, we just take the sum of the maximum sustained winds squared for each 6-hour interval in a storm. So you can think of this as an integral of wind speed over time. And what this means is that longer lasting storms, as well as stronger storms, contribute more to the value of ACE. Another thing I did for this study is that I only considered storms below 30 north. And this is because when storms get north of 30, they tend to undergo baroclinic influences, and they can strengthen or develop under processes that aren't exactly tropical. So in order to get a pure tropical subseasonal signal, I'm really only measuring ACE in the tropics. And also sort of along those lines, I'm only calculating ACE from August through October, partially because that's peak season, and also so that I can avoid some of those baroclinic influences that occur on the tail ends of the season. So for the MJO, in order to measure the MJO, I'm using a parameter called outgoing long wave radiation, or OLR. And this is a measure of convection based on cloud temperature. So vigorous thunderstorms reach higher in the atmosphere, and higher up in the atmosphere it's colder, which means that these thunderstorms release less radiation and their cloud tops are colder. So these cool colors here in this plot on the right indicate more thunderstorm activity. And so this figure here shows the composite OLR for each phase of the MJO. And so we can see for phase 1 and phase 2, there's thunderstorm activity over the Indian Ocean, but there's also maybe a bit of thunderstorm activity over the Atlantic, indicating maybe maybe that's favorable for hurricanes. So in particular, I'm using the real-time OLR MJO index because I'm looking at forecast data. And that uses two empirical orthogonal functions to determine the phase of the MJO. And unfortunately, I don't have time to go over what those are, but they're lots of fun. All right, I'm almost done with methods, but this one's my pride and joy. This is ACE by year, or ABBY, and ABBY is a method to draw out a subseasonal signal by using a conditional composite. So I'm going to go over my thought process while developing this method. So first I should explain these figures here, at least these three figures on top. These show the accumulated cyclone energy over the course of 3 different seasons. And so say I wanted to figure out what are the environmental parameters that are associated with tropical cyclone activity. I could take a composite of environmental conditions when tropical cyclone activity is at its peak. So basically during these 3 periods. But what I would get there, you'll notice, is basically a composite of conditions during September. And so what I would be measuring is the seasonal cycle of the Atlantic hurricane season. And that's useful, especially if you're trying to make, say, like a climate index, but that's not actually what I'm looking for. I want to measure a subseasonal signal. So the next step that I did is I took the normalized anomaly of the ACE, and so you can see that on these 3 figures on the bottom. And so if I take a composite of the peak normalized ACE anomalies, you'll see that I sample 2008 quite a bit. And 2008 was a La Nina year. And so what I would be measuring here is sort of the seasonal oscillations, and I would get what are the conditions associated with El Nino. And that's also useful if I were measuring seasonal tropical cyclone activity, but I want to measure subseasonal tropical cyclone activity. So I have to take one more step. And so what ABBY does is it takes a composite of a set number of events from each year. So it would be as if I took a composite of each of these little circles. And my hope with ABBY is that it would pull out the subseasonal, or the environmental signal associated with subseasonal variability of tropical cyclone activity in the Atlantic. So I did just that, and I did that for a lot of different parameters. So I looked at shear and vorticity and relative humidity, and I looked at some combined parameters such as potential intensity and genesis potential. And as it turns out, the ABBY composites for these different parameters didn't really show all that much. And that's kind of counterintuitive, because that suggests that on weekly scales, if the environment is favorable for Atlantic tropical cyclone activity, you aren't necessarily more likely to get Atlantic tropical cyclones. The exception to this, though, is shear. So one of these did have a signal, and thank goodness. So this is the ABBY composite of shear anomalies in association with subseasonal tropical cyclone activity in the Atlantic. And so you can see there's lower than average shear over the Caribbean and kind of extending off into the main development region. And this makes sense because lower shear means that tropical cyclones are more likely to develop or become stronger. However, just north of this region of low shear is this region of high shear. And that's less intuitive, but it is a significant signal. And in fact, this, at least in this plot, this signal seems to be a lot more important. This high shear signal is also important for subseasonal tropical cyclone development. And if you get nothing else from this talk, I want you to know that this pattern of low shear in the Caribbean and high shear in the Florida, Bahamas, Bermuda region is important for subseasonal activity in the Atlantic. So next I want to see where is this subseasonal shear signal coming from? And one culprit is the MJO, because that's really the only subseasonal game in town. And so this top left figure shows the MJO phase 1 and 2. So remember, MJO phase 1 and 2 is favorable for tropical cyclone activity in the Atlantic. And so this is the shear anomaly associated with MJO phase 1 and 2. And we can see that there is lower shear in the Caribbean and extending into the MDR. And there is sort of a signal of higher shear in the subtropical Atlantic over the Florida, Bahamas, Bermuda region. And so it seems that some of the shear signal might be associated with this favorable MJO phase. And then for completion, I also showed the shear anomaly associated with MJO phase 5 and 6, which are unfavorable for TC activity in the Atlantic. And you can see lots of shear over the tropical Atlantic. So what I want to do is I kind of want to remove this MJO signal. And so what I did next is I took a composite of the Abbey cases that also occurred during MJO phase 1 and 2. And so this is the signal for anomalous shear when there is enhanced subseasonal tropical cyclone activity and we're in MJO phases 1 and 2. And I did that also for MJO phase 5 and 6. And my next step to remove the MJO signal is I subtract these MJO shear anomalies, or I subtract these plots circled in red from these plots circled in purple. And so hopefully what is left over is the subseasonal shear signal associated with tropical cyclone activity that is not dependent on the MJO. And what we see is that there is still a signal of low shear in the Caribbean and higher shear in this subtropical Florida, Bahamas region. And that is the case whether it's MJO phase 1 and 2 or MJO phase 5 or 6. And so what this means is that some of this shear signal of low shear in the Caribbean and higher shear over the Bahamas is independent of the MJO, which suggests that it might be useful as an additional predictor. And we'll see that come up later. So if some of this component isn't the MJO, then what is it? And so it could be related to potential vorticity streamers, which is work that's been done by Philippe Papin. And what PV streamers are these sort of mid-latitude intrusions, which are associated with Rossby wave-breaking events. And so I'll go over a bit of that in my future work, but there is a physical mechanism that might be contributing to this shear pattern that isn't the MJO. All right, so next, I'm going to look at these MJO and ENSO nonlinear interactions. And this plot I have here shows the tropical cyclone activity associated with both MJO phase and the ENSO state. So if you'll remember, during MJO phases 1 and 2, we expect there to be more tropical cyclone activity, so we'd see red during these phases. And during La Niñas, or cooler ENSO states, we expect there to be more tropical cyclone activity, so more red down in this bottom portion of the plot. But what we see isn't quite that. So if it was just a linear combination of MJO and ENSO, we expect that MJO phases 1 and 2 in a La Niña would be incredibly active. But instead we see that it's actually kind of neutral. In fact, these two bins here actually show below average activity, even though both MJO and ENSO would suggest above average activity. And so we see, instead of a combination, ENSO actually kind of causes a shift in favorable MJO phase. So as we get into stronger La Niñas, the favorable MJO phase for tropical cyclone activity kind of moves into phase 3 and then maybe even phase 4 and 5 if you have a really strong La Niña. Another takeaway from this plot, which isn't exactly a new finding, but it's still interesting, is that the variability of tropical cyclone activity with MJO phase increases as we move into cooler ENSO states. And so the reasoning behind this is that the Atlantic is kind of a marginal basin. There isn't much tropical cyclone activity much of the time. And so if there's an El Nino, activity is just shut down across the basin pretty much unanimously. And there's nothing the MJO can do to overcome that. But as conditions get progressively more favorable for cooler and cooler ENSO states, the MJO has more influence on tropical cyclone activity in the Atlantic. And so these are probability density function plots. These are essentially the same as the plot before, but I think these show just a bit more clearly that there is this shift in favorable MJO phase with ENSO state. So I'm starting to work on maybe applying these findings into a predictive framework. And so the first thing I did is create a shear index. And to do that, what I did is I took the area average anomalous shear over this subtropical Florida Bermuda region, and I subtracted the shear anomaly over this Caribbean region. And so hopefully, based on the Abbey composite that I showed earlier, this will correlate very strongly with Atlantic tropical cyclone activity. And so, of course, I tested that. And we see on this plot on the left, this is a scatter plot of the observed values of the shear index, or the reanalysis values of the shear index, with the normalized ACE anomalies. And so if you just look at the red dots, that looks like kind of a mess. It's just a cloud. Maybe you can tell that there's a positive slope, but it really wouldn't be terribly evident if I didn't draw this linear trend line there. And unfortunately, that's just kind of how it is with subseasonal prediction. You don't really have a lot of confidence in the forecast, and you see a lot of variability. But that doesn't mean that we still can't gain something from that. So in order to make this plot maybe a bit more encouraging, what I did is I calculated the odds of an above average 5-day ACE period as a function of the shear index. And so this plot on the right is a direct derivative of this plot on the left. It's just counting what % of these dots fall above 0. And you can see that when the shear index is very low, like below -10, there's a less than 10% chance that the Atlantic is going to see an active period. But as the shear index increases, the odds of an active Atlantic increases, so that if your shear index is 10, you have a more than likely chance that the Atlantic will be active. You can kind of ignore this tail at the end. That's just kind of a function of the fact that there's not very many cases over here. So one thing you might notice is that we don't ever get very confident that we're going to have a very active Atlantic, and that kind of goes back to the fact that the Atlantic is a marginal basin. And in fact, most of the time, the Atlantic is below average, which is interesting. So now that I have a working theory and several predictors that I can use, I'd like to make some forecasts with that. And for that, I'll be using the Navy-ESPC. And so that stands for Navy's Earth System and Prediction Capability Effort. And this model is a fully coupled land, sea, ice, and atmosphere model. As a part of SubX, it makes 45-day forecasts 4 times a week with a resolution of 60 vertical levels. There's a 37-kilometer spatial resolution and 3 hourly data. Previous studies have shown that Navy-ESPC is skillful in predicting the MJO out into subseasonal timeframes, and that it can accurately capture TC activity in association with the MJO. So there's some evidence to believe that the Navy-ESPC will be helpful in these subseasonal predictions. So before I just dive into seeing how well the Navy-ESPC does, I'm going to give it a litmus test, like a really low bar, just to see if it can correctly resolve the physical connection between the shear pattern we saw earlier and tropical cyclone activity. And for that, I'm going to be using Abbey again. And so previously, I used Abbey to take a composite of conditions during the top third of subseasonal ACE events. And I did that reanalysis data. I'm going to be doing the same thing, but except I'm going to be taking composites of forecasts. And this will be a bit complicated by the fact that forecasts have different lead times, so there's going to be several ABI plots that I'm going to show you in a bit. So here, this bottom plot shows the ABI shear pattern that we saw in reanalysis: low shear in the Caribbean, high shear north of the Caribbean. And this bigger plot on top shows the ABI shear pattern associated with the Navy-ESPC 5-day lead time forecast. And we can see it captures the pattern pretty well. We see lower shear in the Caribbean, higher shear in this subtropical region. And I have highlighted here the box that I use for the shear index. So it appears for a 5-day forecast, the model can capture this connection between the shear pattern and tropical cyclone activity. For a 10-day forecast, this pattern weakens some, but is still there. So a 10-day forecast from the Navy-ESPC still captures this lower shear in the Caribbean and higher shear over the Bahamas is associated with tropical cyclone activity. For a 15-day forecast, this pattern really starts to kind of dissolve. There's still lower shear in the Caribbean. This higher shear region over the Bahamas, though, isn't really apparent. And then by 20 days, the pattern is completely gone. The model does not correctly resolve this ABI pattern. And so what we can expect from this is that the model should be useful in predicting tropical cyclone activity, at least out to 10 days, maybe 15 days. And so I looked at that. And so these are the, these plots show the percent chance that the Atlantic will experience an above average tropical cyclone period as a function of the forecasted shear index. And so these 4 different plots are for 4 different lead times. And so we can see with the 5-day lead time, there's a very steep slope, which suggests that there's a strong connection between the predicted shear index and the actual resulting tropical cyclone activity in the Atlantic. And this is a good sign, but this is also in weather scales. So we're already pretty good at forecasting during this lead time. For lead times of 10 days, we still see a positive slope, and in fact, a pretty consistent positive slope. It's not quite as steep as the 5-day lead time slope because forecasts tend to get worse over time, but this is definitely still useful. And at 10-day lead times, this is when weather models start to do really poorly, and we start to get into subseasonal timeframes. So it looks here that the Navy-ESPC forecast for shear index will be useful in predicting tropical cyclone activity, at least for 10-day lead times, and starting to get into subseasonal lead times. And then we get into day 15 and 20. And here the forecasts don't really make much distinction. Perhaps if you squint, or perhaps if I added a few more cases, we could convince ourselves that there's a weak connection between the predicted 15-day shear index forecast and the observed tropical cyclone activity in the Atlantic, but that's not a very convincing line. And then at 20-day lead time, I didn't expect there to be any skill, and there really isn't any. So I guess it's good that the model failed when I expected it to. So the model does, this predicted shear index does seem to be useful in the model. So my next step is to make a multiple linear regression model. And so what this means is that I'll be adding a bunch of different predictors into one linear model. And so I'll add things like ENSO and MDR SSTs and the EOFs of MJO. And so this does 2 things. First, because I'm now drawing from more different sources of predictability, hopefully I get a better model. But the real purpose for why I'm doing this is so that I can compare the skill that is introduced by each of these different parameters. And so I showed with the ABI MJO plots a few slides ago that this shear index pattern seems to be independent from the MJO, and hopefully it is. But it is possible that this shear is just sort of a symptom of the MJO, and that I'm not actually getting any additional skill. I'm just found another way to measure the MJO. But this multiple linear regression model will tell me whether that's true or not. And so for this case, I'm making this multiple linear regression model using reanalysis data to assess the optimal predictability. And so this is a scatter plot of the multiple linear model prediction with the normalized ACE anomaly. And again, this looks very cloudy, a lot of scattered points. But actually, this is the most promising result I've seen yet, that there's an R-square value that is 0.1, and that's the highest R-square value that I think I've encountered in my entire research. And so that suggests that this multiple linear regression model is at least relatively skillful in predicting tropical cyclone activity in the Atlantic. And this plot on the right here is the probability plot, like the ones that I was showing earlier, and it shows a very nice, steady increase. So as the MLR model prediction increases, we see a steady increase in the odds of experiencing an active period in the Atlantic. But now to dive into the nitty-gritty of the model, I want you to focus on the coefficients. And so the magnitude of these coefficients will tell us how important each parameter was in the MLR, or how much each of these parameters contributed to the predictability. And so right off the bat, we see main development region sea surface temperatures seem to contribute the most. And our shear index, unfortunately, looks like it doesn't contribute very much. But this was before, this is just taking the raw values for all of the predictors. I haven't normalized the anomalies here. And once I do that, I get these kind of values. And you'll notice that all of these values are about the same magnitude, which means that all of these predictors were useful. So everybody can get a participation award. But if I had to hand out medals, El Nino or ENSO seems to be the most important predictor. And then actually number 2 is my own shear index, which is awesome. That means that I've hopefully created a parameter that is going to be useful for subseasonal prediction of Atlantic tropical cyclone activity. And then just for fun, so I mentioned SubX, or hopefully I mentioned that SubX creates real-time forecasts. And so I thought I would play around with those during this hurricane season, and I thought I'd show you an example. So here, this is a shear forecast that was initialized on July 21st, 2020. And it was a 10-day forecast, so it verified on July 30th or 31st. And so we can see this shear forecast shows below average shear in the Caribbean and kind of neutral, maybe you could argue some above average shear over Florida, the Bahamas, Bermuda region. And so the shear index here was very positive, or relatively positive, about 5, which would indicate that we're more likely, at least more likely than average, to see tropical cyclone activity during this July 31st period. And as it so happened, on July 31st, Isaias became a hurricane over the Bahamas. And so this was a relatively long track, although still somewhat weak hurricane, but certainly contributed to this July 31st period being above average in tropical cyclone activity. One interesting thing that I like to draw from this is that there's a competition of scales here. So a subseasonal forecast that favors tropical cyclone activity is high shear over the Bahamas and Florida. And indeed, Isaias encountered a bunch of high shear over this region and subsequently weakened. And so even though this high shear pattern is favorable on subseasonal scales, it is detrimental on weather scales. And so it's kind of interesting to see this interplay between the two carry out kind of in real time. So in conclusion, the MJO and ENSO combine non-linearly, causing a shift in MJO phase that favors tropical cyclone activity. And in fact, as ENSO gets towards progressively cooler phases, the MJO becomes more important in determining tropical cyclone activity. Also, vertical wind shear is one of the only environmental parameters with a strong instantaneous connection to subseasonal Atlantic tropical cyclone activity, and therefore may be useful in prediction. And I showed that Navy-ESPC the Navy-ESPC predictions of the shear index appear to have skill in predicting Atlantic tropical cyclone activity at least out to 10 days, potentially out to 2 weeks. And I showed that the shear index, if predicted perfectly, would contribute skill to a multiple linear regression model, showing that this shear index is not just another way to measure the MJO. So the future work, and in fact, sort of current work, is creating a statistical model based on the predicted values of the MJO, MDR, SSTs, and so in the shear index. And so based on the results that I showed you today, since the shear index seems to be a useful predictor out to 10 days, hopefully it will remain useful as a predictor out to 10 days in the multiple linear regression model, but I still need to crunch the numbers on that. So that's the immediate next step. Some other steps that I'd like to take are expanding the predictions to incorporate other predictors. So I mentioned Philippe Papin's work with PV streamers, and he's actually created a PV streamer index to measure PV streamers over the Atlantic, and in fact has assessed the PV streamer forecast from the Navy-ESPC. So I'm going to ask him for that data, and hopefully I'll be able to incorporate that into my subseasonal prediction. Another parameter that I might look at is relative humidity. So I didn't show that result today, but there actually is a small signal in relative humidity over Africa 10 days in advance of Atlantic tropical cyclone activity. So perhaps I'll make a predictor out of that. So once I've explored the possible predictors, I'd like to look into the physical mechanisms that are behind these predictors. So I mentioned Rossby wave breaking as being connected to PV streamers. And so understanding the mid-latitude pattern might be crucial in understanding sources of subseasonal predictability of Atlantic tropical cyclone activity in the Atlantic. And another step, not one that I'm immediately going to take, but one that would be a good step for operational people, is to incorporate other sub-X models. So there are all these other models that hopefully have some skill in subseasonal prediction. And so perhaps by assembling them into a multi-model ensemble, maybe we can get better shear index predictions, and maybe we can improve tropical cyclone activity predictions out to 15 days, which I wasn't able to do here. So that's all I had for you guys. Do you have any questions?
All right, thank you, Kurt. Big virtual round of applause. All right, if anybody has any questions, you can ask them yourself and turn on your video. Otherwise, you can put them in the chat.
Hey, it's Dave Nolan. I have a question.
Yeah, go ahead.
Is there a particular synoptic pattern, like a shift of the Bermuda high or a trough, ridge pattern that you can associate with the positive or negative phases of your shear index?
That's a good question. So I haven't actually looked at sea level pressure in my ABBY plots or in association with the shear index. So I don't really have an answer for you, but that would be interesting to look at, because it does seem to be associated, or if the PV streamer theory is correct, then these frontal passages and maybe these low pressure systems over the North Atlantic would be an important indicator of subseasonal TC activity.
I have a question.
Yeah.
So do you think that, so this may be just, I have no idea, but, ACE is going to be biased towards, the long track, really intense systems. So do you think maybe you could be missing something if you tune it to ACE, and maybe are there other indices that could just show you if a TC forms? I'm just thinking of this year because we've had so many of those marginal sort of systems.
Yeah. So I think it's funny you asked that, because I think Brian McNulty asked last year, why don't you just look at major hurricanes? And so, because those are the storms that we really care about. And I think ACE is ACE is the happy medium, because we really do care about like the long track systems that cause lots of damage, but like this year, there were a lot of relatively short-lived tropical cyclones in the Atlantic. And so I think ACE is the best way that really weights tropical cyclone activity towards the more destructive storms, but still includes the short-lived storms.
Can I ask one more question? If no one else has any?
Sure.
So one thing I'm curious about is, if you have like a low shear environment or favorable environment, you still probably need some incipient like disturbance or something to organize. So I'm wondering if like some sort of like in your background, sort of when you did the El Nino and MJO, if there's any sort of way to sort of look at cases where you do and you don't have incipient disturbances, if that makes sense. So yeah. Like if you have easterly waves that are coming off of Africa into that environment, it may be more favorable than if it's just kind of a
yeah. So I did mention African easterly waves at the beginning, but I didn't really touch on that later. But one thing that I did want to do, and one thing that I think could be added to this research, is looking at variability in African easterly wave intensity. But there was no easy way to do that early in my research, and I still don't think there's really an easy way to do that because you're tackling that, and I think you've had some difficulty. But yeah, that would be a tremendously helpful contribution to this research, because there has been evidence that the MJO modulation of African easterly wave activity is what is important for the subseasonal variability in the Atlantic.
Yeah, that'd be cool if there was an easy way to do it, but.
I have a question.
Yeah.
Nice job, Kurt. So you had mentioned that the interaction between the MJO and ENSO is nonlinear, but you're using a multiple linear regression model to analyze it. So I was wondering if you could explain a little bit more how you chose that, and if you think taking a nonlinear approach would help increase that R² value, if it's not worth it, if you could just explain that linear versus nonlinear a little bit more.
Yeah, so that was definitely something that I considered and maybe even struggled with because so I chose a multiple linear regression model just because it's the simplest. And I was thinking of ways that I could maybe easily combine this nonlinear MJO ENSO interaction, but that's a relatively new finding, and there's also just not very many cases of it. And so I was worried that if I tried to account for this nonlinear interaction, I would end up overfitting this model. But I was still hoping that there was a way that I could maybe get around that, perhaps considering only neutral ENSO cases so that I don't have this nonlinear variability would be an interesting way to more accurately assess the multiple linear regression model.
Cool. So we have a question in the chat from Song-Ki Lee. They say, hi, Kurt, have you considered thermodynamic predictors such as CAPE, lifted index, or OLR in addition to the wind shear?
Yeah, good question. Thanks, Song-Ki. So I haven't looked at any of those specifically. However, I have looked at potential intensity, which does incorporate CAPE. And I found that it does not correlate very well with tropical cyclone activity. So I've indirectly considered those, and it wasn't promising, but perhaps I could revisit OLR because that might be interesting, and I did point that out earlier in the talk.
Cool. They say thank you. Does anybody else have any questions? All right, if not, let's give Kurt a round of applause again. He did a great job. Woo! All right, everybody, we'll see you tomorrow, not tomorrow. I should know this. We'll see you next time at the next Compass seminar. All right, bye everybody.